Hello there! Now we're going to show you actually sketching a plot of a function. So now let's try to sketch this curve. F of x equals 2x cubed minus 3x squared minus 12x. The first step is perhaps to find the y-intercepts. Well, let's see. What are the y-intercepts here? It's exactly where f of 0 is. And this isn't too hard. So f of 0 is equal to 2 times 0 cubed minus 3 times 0 squared minus 12 times 0, and that's just equal to 0. So that's the y-intercept. It has a y-intercept at 0, 0. So let's see. There. That is a point on our curve. So next, we're going to compute f prime and f double prime. We can do them both at once. So look at this. So we know that f of x is equal to 2x cubed minus 3x squared minus 12x. So f prime of x is equal to 6x squared minus 6x minus 12, and f double prime of x is equal to 12x minus 6. Very easy. All right, so now we're going to find the critical points. And recall that while the word critical point in English might seem like it means something important or something like this, in mathematics, critical points have a very specialized meaning. And that is where the first derivative is 0 or where the first derivative is undefined. Fortunately for us, the first derivative looks like this, and so it's defined for all real numbers. So all we really need to do is check and see where this is equal to 0. So let's write 0 is equal to 6x squared minus 6x minus 12. So the first thing we do is we divide everything through by 6, and we get 0 is equal to x squared minus x minus 2. And now, I can't factor much, but even I can factor this. Let's see, it factors as x. It's going to be x minus 2 times x plus 1. And this means that this quadratic expression here has roots when x is equal to 2 and when x is equal to negative 1. Now let's look at this on the plot. What I like to do here is I like to make a big vertical line. This is where the critical point is. It's at x equals 2 and x equals negative 1. And I like to make the vertical line because all you know is that the direction of f of x may or may not be changing, but it's the same between it, so you don't really know the height. This is what I like to do. All right, so we have this, and now we need the check points because we want to know, is f of x decreasing or increasing here? Decreasing or increasing? Decreasing or increasing? Well, let's check some points, okay? And so look, a good point to check over here is negative 2. Let's check negative 2, and we'll check out the first derivative. And so we have the first derivative of negative 2. Here's the first derivative written. It's going to be 6 times negative 2 squared minus 6 times negative 2 minus 12. Now check this out. This is kind of cool. This is equal to, well, negative 2 squared is 4. 6 times 4 is 24. And 6 times negative 2 is minus 12, but it's negative minus 12, or minus negative 12. And so that's going to be plus 12 minus 12. These will cancel. This is equal to 24. But most important for this discussion is that it's positive. And so what this means as far as our graph is concerned is that the function is increasing until this critical point. All right? So now we're going to check another point. We're going to check 0. Because that's an easy point to check, and it's between the two critical points. So f prime of 0, is equal to negative 12. I don't even need to do any calculations there. And so it's negative, which means the function is decreasing here. And then let's see, f prime of 3. Well, this looks a little harder, so it's going to be 6 times 3 squared minus 6 times 3 minus 12. Okay, well, let's see. 6 times 3 squared. 3 squared is 9, and 6 times 9 is 54. Minus 18 minus 12. Well, let's see. Minus 18, negative 18 minus 12 is equal to minus 30. So this is equal to 54 minus 30, which is equal to 24. Aha. So that's important to this discussion, positive, which means that our function is increasing. There we go. So it's increasing, then it's decreasing, then it's increasing. Okay, great. So what we in particular what we see here is that we have a local maximum here and a local minimum here. Let's see if we can figure out the values at the local max and local min. And to do this, what we're going to do is we're going to plug in the critical points into the initial function. And so let's see. This is going to be 2 times 2 cubed minus 3 times 2 squared minus 12 times 2. Okay, well, 2 times 2 cubed, that's 16. 3 times 2 squared is, well, that's going to be minus 12. And 12 times 2 is 24. Okay, let's see. Well, negative 12 minus 24, this is equal to 16 minus 36. This is equal to negative 20. Okay, so we should put maybe way down here, negative 20. There's a point on our function. And let's see what's going on here. Aha, this is the other critical point, negative 1. So f of negative 1, well, that's 2 times negative 1 cubed minus 3 times negative 1 squared minus 12 times negative 1. Let's see, negative 1 cubed is just negative 1. Times 2 is negative 2, minus 3 here, and then this is going to be plus 12. Let's see, 2 minus, this is equal to negative 5 plus 12. This is equal to 7. So at negative 1, our function is equal to 7. And looking where 20 is, I should probably put this somewhere here. And so that's supposed to be 7. All right. There we go. And so now we need to find candidates for inflection points. Now you may be thinking that inflection points are just the critical points of the first derivative. That's not the case, unfortunately. That would be great, but it's not the case. You know, the inflection points are different. They are where the concavity changes. But to find the candidates, we should first see where the second derivative has a 0, where it has a root. Okay, and so I write 0 equals 12x minus 6, so 6 is equal to 12x, so 1/2 is equal to x. And I should mark this on my graph. I should mark the inflection point. So the inflection point is going to happen at 1/2. That's right between here. And so this is where the concavity changes. And I want to know then where is it concave up and where is it concave down. And the way I'm going to find out is I'm going to check concavity by checking points. And the easy points to check are, let's see, 0 is right to the left of this line, so we can check 0 and we can check 1. Let's go ahead and do that. So if I can pick up this piece of paper, there we go. So f double prime of 0 is equal to 12 times 0 minus 6 is equal to negative 6. Okay, so negative 6. That means that our function is concave down, and so it's going to look something like this. This is concave down to the left, and let's see, f double prime of 1, well, that's equal to 12 minus 6, which is equal to 6, and that's positive, which means it's concave up here, concave up. There we go. That's looking really nice. right? And so, yeah, so we're getting our curve sketched. Now what's going on here? So, finally, if possible, find the X-intercepts. Now look, the X-intercepts, this means solving an equation. That's hard in general. Now, in this case, we can actually do it, but I'm going to leave most of it to you to do on your own. The one thing I will say is we do have one solution to our equation already. Here it is. But at this point, we can actually complete the plot, and I'm going to go ahead and do that, or the sketch of the plot, rather. So it's going to be concave down till we get to this local maximum right there, and then it's going to go back down, and it has to go through this point here. You got to say concave down, and then I'm going to change concavity. Then there's the local minimum, and then I'm going to come back up, and there's the sketch of my plot. So we plotted a function. You can actually see the same example in the textbook. Maybe some of the steps are done slightly differently, but it's basically the same idea. All right? Time to do some more math.